Okay, well, it's 8 o'clock, I think. Yes, it is. Okay, so let me just make some announcements. All right, so the homework that was due Friday is now due this Friday. Okay, because of the storm and all the mess and everybody's problems with evacuating and whatever. Okay, homework that was due Friday, last Friday is now due this Friday. If you have already handed it in, that's great. If you've handed it in and you want to go back and make some changes, you can do that too. But make sure you send it to our class email, which is judyK Calc2413 at yahoo.com. Okay. And also make sure you submit it as one PDF file and that we can read it.
So send it in through the email listed on Blackboard.
The
one that says to return.
I don't know what's listed on Blackboard. The one that's listed in your syllabus, which is on Blackboard. Okay. I have a Lamar email address. I also have a Gmail address that I use a lot, but I do not want you corresponding with me through those because your messages get all mixed up with all my other messages and it's just too much to deal with. If you'll use our class email, which is JKCALC2143 at yahoo.com, I would really appreciate it. I'm not guaranteeing you that if you send it to my Lamar address or my Gmail that I'll even see it. Yeah. Everything is now on Blackboard, okay? The homework assignment, the syllabus, class notes from every day. I posted a sheet with limit laws yesterday. That's now on Blackboard. There are a lot of things on Blackboard now. They're all items. And in fact, we're only in the second week of class and it's getting to be a lot. But they are in chronological order, more or less. So that should help you find things.
I'm gonna share the screen for a second. I'm on Blackboard page at the emails where it says to send them to, and I wanted you to see if these are the right ones.
Okay, Mr. Miller, how do I share the screen again?
I can share the screen. I've got it says screen.
Well, I think you'd have to do settings.
Okay.
Yeah.
Let's see. So
it's allow participants to share screen.
Oh, I didn't know that she had disabled it. Sorry.
No, I will enable it. Let me figure out how to do it. Okay.
I am so sorry. I thought it was just by default we could and no one was trying to.
Where's settings?
It should be at the top right-hand corner of the screen.
Top right-hand corner. Okay. Under more. No.
I can just read if you can still hear me.
No. Okay, wait a minute. Let me record now. And share content. Okay, we did it yesterday. Where is settings? Zoom. Okay, nope.
It's fine. I can just read the email it says here on the thing and you can verify it.
Yes, Daniel, we had class yesterday. Okay, could you read it for us?
Sure. The email it says here where to submit to is JKCAL2413 at yahoo.com or am761624 at gmail.com.
Okay, yeah, that's so that Mr. Miller is going to be grading your homework. The first one should be JKCALC. Is there a C in there?
JACALC. JKCALC. Yeah.
Yeah, okay. That one. So yeah. Yeah, there's also homework submission. There's a little thing on homework submission. That's on Blackboard. That gives you instructions, tells you where to send it. Okay? Any questions?
Well, ma'am, if you don't mind my asking, since next Monday is Labor Day, will we be having class that day?
No,
Okay, thank you.
that's a holiday. Somebody asked about grades. Let's not worry about that yet. Okay. Okay, yeah. All right, let's get started. I have been having some problems with this thing jumping all over the place this morning, so I hope it'll stop. I clean the screen, hoping that would help, but we will see. Okay. Okay, so can everybody see the screen now? Yes, no?
Yes, ma'am.
Yes.
Okay, great, thank you. All right, so we're going to talk about horizontal and vertical asymptotes and infinite limits first. This will just help you with problem number 4 in your homework, but it's not really that new. You've seen the idea of horizontal and vertical asymptotes before, but okay. So first, let f be a function that's defined on an open interval containing the number a, except possibly at a itself. Then you say the limit as x approaches a is infinity. There we go. So right here, that means that for every positive number m, think big positive, there is a positive number, okay, that should be a number delta, such that f of x is greater than m whenever x is within delta of a. That's, but not equal to a. That's what that last line says. Okay, and we can define the one-sided limits according to the same way, only, okay, if x is approaching a from the left, you're only going to take x's that are less than a. If x is approaching a from the right, you're only going to take x's that are greater than a, but you can define those. And you can always also define the limit is approaching a is minus infinity in a similar way, and also the one-sided limits. Okay, so here's an example. The limit as x approaches 0 of 1 over x squared is infinity. And rather than try to prove this exactly, let me just show you that it's plausible. I'm going to graph this, and I'm going to take some x's close to a, which is 0 here. So how about 0.1, 0.01, 0.001, and then go on the other side, minus 0.1. Well, in fact, I can just, yeah, it's just been jumping all over the place this morning, and I don't really understand why. I can do both at the same time because I'm going to square these numbers. Okay, well, if x is plus or minus 0.1, then I've got 1 over 1/10 squared, which is 1 over 100, which is 100. And if I've got 0.01 plus or minus, that's 1 over 1/100 squared. That's 1 over what? 1 over 10 to the 4th, which is 10 to the 4th, and so forth. If I take 0.1 over, that's 1 over 1,000 squared. That's 1 over 10 to the 6th, which is equal to, oops, that's a 1, which is equal to 10 to the 6th. And you can see these numbers are getting big pretty fast as I come into 0, okay? In fact, the graph, okay, it's not supposed to touch that y-axis. It gets really close to the y-axis, but never touches it. Let's see if I can do that better. Well, okay, it looks like that. It's symmetric about the y-axis. So here, the limit as x approaches 0 of 1 over x squared is plus infinity. Because as you come in from the left or you come in from the right, 1 over x squared is getting big without bound. That's what this definition says. You can actually prove this with some inequalities, but I think we'll just stick with the numerical evidence. And you say in this case, okay, this function 1 over x squared has a vertical asymptote. At x equal to 0. Here's another example, in fact, similar, but this one's got, okay, what happens coming in from the left and coming in from the right is different. I think I'll just sketch this. 1 over x is positive, looks like this. And 1 over x, if x is negative, looks like this, okay? So coming in from the right, your f values are getting larger and larger and larger. So you get that the limit as x approaches 0 from the right of 1 over x is infinity. And coming in from the left, so that's coming in this way, well, your f value is getting large in the negative direction. So the limit as x comes into 0 from the left of 1 over x is minus infinity. Now, again, if a limit is infinity, it does not exist because infinity is a number. When we write that the limit as x goes to 0 from the right of 1 over x is infinity, we're saying something about how the limit fails to exist. It fails to exist because those numbers 1 over x for x close to 0, but x bigger than 0, they are very, very large, and those closer you get to 0, the larger they are. They are increasing without bound. Okay. Yeah, there are other ways a limit can fail to exist. This just kind of narrows it down. Yes, and okay. This function 1 over x has a vertical asymptote at 0. Okay. Yeah, okay. Let me just say a little bit more about this. Let's just make a rule or fact. The limit as x approaches 0 from the right is plus infinity. I'll just say what r is in a minute. And the limit, okay. Okay. The limit as x approaches 0 from the left, 1 over x to the r. Well, okay. It's either plus infinity or minus infinity, depending. And also for this bottom one, you have to worry about when x to the r is defined. Sometimes it's not. For example, if r is a half, you can't talk about the square root of -1 because we're not going to talk about complex numbers in here. But this limit's always plus infinity or minus infinity, provided it exists. And in general, if the function f, let's see, has a vertical asymptote at x equal to a if the limit as x approaches a from the right of f is plus or minus infinity, either one, or the limit as x approaches a from the left of f of x is either plus infinity or minus infinity. If one of those one-sided limits is either plus infinity or minus infinity, f has a vertical asymptote at that number, okay? And well, and for these two pictures, x equal to 0 is the vertical asymptote. X equal to 0 here is a vertical asymptote. But it can be more complicated than that too. Let's see. Can I give a nice example? How about this? And suppose we look at f of x equal to 1 over x squared minus 3. Well, that's equal to, I don't need to write that. Okay. All right. What's the domain of that function? Can somebody tell me?
It will be every number or all real numbers except the one that when multiplied by itself would result in a positive 3.
Yes. That's a very good answer. Very precise. Okay, yeah, you don't want x squared minus 3 to be equal to 0. That x is not in the domain. And let's see, when does that happen? X squared minus 3 is equal to 0 says that x is either plus or minus the square root of 3. So there are two numbers at which that function is not defined. And of course, now I run out of room as usual. This one's got two asymptotes. Yeah, a lot of times if a function is not defined at a number, it's got an asymptote there. In this case, that's true in this case. What does it look like? Let's see. If x is, say, 3, I get 1 over 6. So positive numbers. And as x comes into 3 from the left, the square root of 3 rather. Let's see, I would get numbers that are close to 9, but less than 9. So that limit's going to be minus infinity. So it's going to get something like that. And if you come in from the right, I'm going to get x squared minus 9 is going to be a small positive number, which is going to make 1 over x squared minus 9 a large positive number. This is minus infinity. This is plus infinity. So, okay, this is, and I guess let's go ahead and get the other two. The limit as x goes to the square root of 3 from the left. Okay, that's going to be, let's see, if I'm to the left of square root of 3, x squared is going to be less than 9, so that's going to be negative. That's going to make that a minus infinity. And then the reverse is going to happen on the other side. And I'm running out of room real fast. Okay, so it's going to look something like, let's see, that's not what happened. That we cross at minus 3. I think the graph is going to look something like that. Okay. So this one's actually got 2 vertical asymptotes. It's got a vertical asymptote. Oops. That has been driving me crazy this morning. Don't really understand why it's happening. Vertical asymptote at x equal to both plus and minus the square root of 3. Okay, so vertical asymptotes can happen, and we also have horizontal asymptotes. Vertical asymptotes happen when you get a limit of infinity. Okay, the limit is infinity, which is not a number. It's either infinity or minus infinity, so a large absolute value. What about taking the limit as x goes to infinity of f of x? Well, first of all, for that to make any sense, your function must be defined on an infinite interval. Must be defined for some number a, and then for all numbers greater than a. Then you can say the limit as x approaches infinity of f of x is L. Well, that's going to mean that the values of f of x can be made arbitrarily close to L by taking x sufficiently large. And likewise, you can define the limit as x grows to minus infinity. And this time, x would have to be defined on an interval that contains all numbers less than some b. So the limit as x approaches minus infinity of f of x is L if the values of f of x can be made arbitrarily close to L by taking x sufficiently large and negative. And in either case here, you say that f has a horizontal asymptote at L. Okay. And okay, this is back to that example we were looking at, 1 over x. Well, I already graphed it, so let's do it again. Graph looks like this. Because, yeah, so it has a vertical asymptote at x equal to 0, but it's also got a horizontal asymptote y equal to 0. in fact, in both directions, because, okay, why is this true? Well, if you take X really large, say X equal to 1,000, 1 over 1,000 is small, right? Small and positive. If I take X equal to 1,000,000, 1 over 1,000,000's even smaller, even closer to 0. So that's why we get this horizontal asymptote, y equal to 0 in this direction, the positive direction. Likewise, you get y equal to 0, a horizontal asymptote in the negative direction. Because if you take, say, minus 1,000,000,000 for X, 1 over minus 1,000,000,000 is a small negative number, pretty close to 0. So 1 over X has y equal to 0 as a horizontal asymptote. And okay, we already noticed that 1 over X has X equal to 0 as a vertical asymptote. Okay, so it's got both. Are there any questions so far? Okay, I don't hear anything, so I'll assume no. Let's take this function, arctan of X. Let's see, did I have anything after this? Yeah, okay, but I don't particularly want to talk. Maybe I don't know if I want to talk about the example or not. Okay, let's graph the arctan of X first of all. It's the inverse of the tangent function, right? And well, how do you get this graph? I'm going to graph the tangent first. Oh, the tangent function has vertical asymptotes at odd multiples of pi over 2. Okay. And so it comes up like this, it comes up like this, and it's doing the same thing on this side. Now, that's a graph of the tangent, but that's not one-to-one, right? Many values give you the same, many x's will give you the same y value. For example, tangent of 0, 0, the tangent of pi, 0, tangent of 2 pi, 0, and it goes on forever. This is not one-to-one, so it doesn't actually have an inverse. But what do people do? They, let's see, they sort of erase a lot of pieces, okay? So we're going to just throw away this piece and throw away this piece for the moment, just so we can define.
Essentially, arctangent means you only take one arc of the tangent at its base point.
Okay, you can think of it that way. Yeah, we only want to take one interval, one open interval. So yeah, so we cut this down. Cut the tangent down to, and okay, everybody agrees it ought to be the interval minus pi over 2 to pi over 2. Okay. So this cut down tangent is 1-to-1. All right. So now we've just got this one piece. Let's see. And I don't know what that line is. I don't know where it came from. But okay. Let's go below it. Okay, so we just sort of threw away those other pieces. And this is a problem sometimes, actually. But we won't get into that now. So we just have this one piece. And that is 1 to 1. Okay. So what we're going to do is flip all the ordered pairs. 0, 0. Well, 0, 0, that's on. So this is tangent. I'm going to call it cap tangent. As I cut it down. 0, 0's on cap tangent, so it's going to be on the arc tangent. And let's see, what are some other values? So now I'm going to flip them over. Well, I don't know many special angles. Okay, pi over 4. I know that the tangent of pi over 4 is 1, right? Because it's square 1 over the square root of 2 over 1 over the square root of 2. So that means that 1 pi over 4 is on the arc tangent. Okay. So for x equal to 1, I'll call that pi over 4. That's going to be on my arc tangent. For x equal to minus 1, going to get, yeah, the tangent of minus pi over 4 is minus 1. So minus 1, if x is minus 1, the arc tangent is minus 4. Call that minus 1. Okay. But if I get close to less than pi over 2, but close, my tangent values are big. So going to in plus infinity. Okay. The fact that the tangent has a vertical asymptote at pi over 2 and the limit as x approaches pi over 2 from the left is plus infinity is going to mean that y equal to pi over 2 is a horizontal asymptote. Okay, because I'm flipping ordered pairs. That is, I'm taking xy and changing it to yx to get the inverse. So that means that I've got a horizontal asymptote at pi over 2. Because my tangent values, as I get close to pi over 2 from the left, they're going to infinity. That means that my arctan, as x goes to infinity, it's going to approach pi over 2. So yeah, the vertical asymptote is now becomes a horizontal asymptote. So I get that over there. And the same thing happens in the negative direction, right? As you go to minus pi over 2 from the right, your y values are getting large in the negative direction. So I'm going to get a horizontal asymptote at minus pi over 2. So it looks like that. And okay, so there's a graph of the arctan, rough graph. But that one has 2 different horizontal asymptotes. It's got y equal to pi over 2. The limit as x approaches infinity of the arctangent of x is equal to pi over 2. So that is a horizontal asymptote. And also the limit as x approaches minus infinity of the arctangent of x is minus pi over 2, which says y equal to minus pi over 2 is also a horizontal asymptote. But this one, okay, has different asymptotes in different directions. The plus infinity, as x goes to plus infinity, you get a different horizontal asymptote as you do when x goes to minus infinity. Any questions?
I have one kind of related to this. How exactly would the arctan relate to cotangent functions?
Well, okay, yeah. The cotangent, you get, okay. Actually, it turns out cotangent and tangent and arctangent and arccotangent, we're not going to really need both of them. But you have no idea whether that's true now. Okay, so let's just see. Well, I'm going to talk in a lot more detail about the inverse trig functions later. But, okay, well, I'm drawing in green. Let's see, the cotangent has vertical asymptotes at integer multiples of pi, right? And in fact, it's 1 over the tangent, so it comes down like, and this actually is an asymptote. So yeah, the cotangent that's very rough. Okay, cotangent of x looks like that. Again, you're gonna cut it down to make it 1-to-1 because this is, you've got all these curves. That's far from 1-to-1. So cut down, oops, and I don't want to do this example anyway, so let me just erase it. Okay, you cut it down, and now we're going to keep this piece, okay? Everybody pretty much agrees that you should keep that piece. There are the secant, people don't agree which piece you should keep. That leads to some confusion. So we're just keeping that one piece. So cotangent x, we're just going to, this is the cut down cotangent. Which I'm going to call cap cotangent. That has, so 0 is less than x is less than pi, defined on that interval. Now it's 1-to-1, and we can talk about the arc cotangent by flipping ordered pairs. Let's see, this is what, pi over 2. And so what would that look like? Well, the vertical asymptote, so that's at x equal to 0 and x equal to pi, become horizontal asymptotes. And let's see, the 0, these are large positive. Those are large negative. So that would be a picture of the arc cotangent. Okay. Yeah, so the arc cotangent has 2 horizontal asymptotes too, but neither one of these two functions, arctangent or arc cotangent, has a vertical asymptote. So they don't always go together. Okay, any more questions? But I'm going to start something new.
Also, someone in the chat said, so what would the function look like for us to find these vertical and horizontal asymptotes? Or what would the problem look like for us to recognize that we're looking for the asymptotes?
For the vertical asymptotes, I would look for, first of all, where is the function not defined? Okay. Now, you don't always have them just because the function is not defined at, say, 3, but that's a good place to look. If, yes. Okay, well, it depends on the problem, and you have to take it problem by problem, but you have a vertical asymptote at x equal to a for the function f. Okay. Why is it not moving? Oh, this thing has been driving me crazy today. What's wrong with this? Well, I tell you what, I'll just start a new one. Vertical asymptote at x equal to a for f. If, okay, one of two things happens. F has to be defined close to a, okay, but the limit as x approaches a from the left of f of x is plus infinity or minus infinity. If that happens, you have a vertical asymptote. Or if the limit as x approaches a from the right of f of x, that's plus infinity or minus infinity. That's when you have a vertical asymptote. So you look for numbers at which that limit is going off the rails is the numbers. Yeah, the limit doesn't exist there, right? Because plus infinity and minus infinity are not numbers. But as you get close to x from one side, doesn't have to be from both sides. If it's just plus infinity, you come in from the left, vertical asymptote, period, no matter what else happens. So yeah, the first thing I would look for, where is f not defined? That's not always sufficient, but that's a good place to start. For horizontal asymptotes, well, okay. You're looking at just two limits. The limit as x approaches infinity of f of x. If that's a number, then, okay, or you have a number there. No, let me not do this. Okay. If the limit as x approaches infinity of f of x is a number L, then y equal to L is a horizontal asymptote for f, period. Okay. And if the limit as x approaches minus infinity of f is m, again, m is a number, then y equal to m is a horizontal asymptote. So yeah, a function can have only two horizontal asymptotes because you're either going to minus infinity to get the L, or you're going to plus infinity to get the L. So only two horizontal asymptotes. It can have as many vertical asymptotes as you please. Okay, does that answer the question?
Also, the same person just put in the chat another question that says, so what would the problem look like? I guess they're trying to see what a formula or a function that would have a asymptote may look like. Is that or what a question relating to one would be?
There is no formula. Okay, no formula. We don't always get formulas. We're not that lucky sometimes. But you're looking at, for vertical asymptotes, you're looking for places. So for vertical asymptotes, you're looking for a number. You're looking for a number where the limit kind of goes off the rails. So you get close to A from one side or the other, the f of x's get real big. For a horizontal asymptote, you're looking at just two things. What happens as x gets large? Does f of x do something? I can draw a couple of pictures, but there is no formula. We don't always get formulas. We're going to do something called integration towards the end of the semester. And there just aren't that many formulas. Okay, so you just have to live with it. Okay, so just some sketches. Here's, well, I was going to do this. I think it was this function. This function has a horizontal asymptote at y equal to 1. And it actually, okay, it has a graph that looks like this. You can kind of see, so yeah, rational functions will quite often have horizontal asymptotes. If the, in fact, it always does, if the power of the polynomial in the numerator is equal to the power of the denominator. Because what happens as x goes to infinity, to x squared minus 1 over x squared plus 1. Well, you're going to have large number minus 1 over that same large number plus 1. Like if x is 1,000. Okay, if x is 1,000, say. Well, this is not a proof. I'm just putting in some numbers. But okay, that's a pretty large x. X squared minus 1 over x squared plus 1 would be, okay, this is 10 cubed. So it'd be 10 to the 6 minus 1 over 10 to the 6 plus 1. Well, that's pretty close to 1, isn't it? It's, okay, 10 to the 6 is a million. So this 10 to the 6 minus 1 is 999,999. And 10 to the 6 plus 1 is 1,000,001. Those two numbers are only 2 1,000,000ths apart. They're pretty close, and one's in the middle. Okay, so this is close to 1. That's how you get that horizontal asymptote. And you can see that it's a negative sometime because of that x squared minus 1. If you put in 0, you get minus 1. Okay, but going in the negative direction, well, everything gets, well, the x's get squared, so you're going to get the same result. So that's a case. Sometimes when you have rational functions, the polynomial on the top has the same degree as the polynomial on the bottom. You will get horizontal asymptotes there. So that's one possibility, but there are lots of ways these can happen. We're going to talk about horizontal and vertical asymptotes later. We're going to start talking about a special kind of limit called a derivative. And oh yeah, before I do that, okay, so this function has a horizontal asymptote. if you've got a function and it looks like this, okay, I just made one up. You have to make up a function yourself, okay, in number 4 in your homework. But okay, this function has no horizontal asymptotes. That's supposed to be an N. No horizontal asymptotes. Because as x goes to infinity, it looks like f of x is going to plus infinity. As x goes to minus infinity, f of x is going to minus infinity. So that's no horizontal asymptotes. Okay, that's the difference. I hope that helps. We will be returning to this idea of asymptotes in great detail later when we start using calculus to sketch the graphs of functions.
So number 4, the homework, we have to sketch one graph and it has to meet all 4 of the things.
Yes, one graph that has all 4 of those properties.
And this is an example of how that graph would end up working. Just
Well, there are many ways you can, so you make up, yeah, and I don't expect you to give me a formula for F, okay? A sketch is good enough. A sketch like this. Now, this
Okay.
is not going to satisfy, this is not going to satisfy, okay. This one's not going to satisfy the properties of number 4. But a sketch like this is all you need to do, give me to define this function. Okay.
That's what
It
I
helps
meant.
if you, okay, it helps to have me some tick marks, okay, because it says certain things happen at certain numbers. So you want to make sure that you have those numbers on your graph and show that the graph does whatever it was supposed to do. Actually, I'm just about out of time. Okay, so I will stop here. Let me just tell you what's coming tomorrow. We're going to talk about something called the derivative, which is a special kind of limit. We're going to talk about, that's K. We're going to talk about, well, calculus is all about limits. Derivatives are limits, integrals are limits, series are limits. Many different limits come up in calculus, and calculus is kind of, it's one way to think about it. It's how you understand infinity, okay? When you can make sense of it and when you can't. That's what we're learning. And okay, so I'm gonna end the session. If you have a question or two, just stick around. Also today, let's see, this is Tuesday, so I don't have an office hour today. I'm gonna put a Zoom meeting in for both classes for 1 o'clock on Wednesdays, okay? I had an office hour yesterday. Nobody came, but I was sitting there, okay? Yeah, so there'll be a Zoom invitation for Mondays at 10:15, Wednesdays at 1, and Fridays, I think, at 11. You do not have to come, but if you want to come and ask questions, you can do that. And okay, so let's see, go back to Zoom. Okay. So if you are, the class is over. If you wish to go, please do. Otherwise, stick around. Maybe you have a question or so we can answer it.
Bye. Have a good day.
Bye.